all the data lives on a two-dimensional manifold, as we could have expected. Now the question is, we know we will learn POD expansion, DMD expansion, and so on. What do they give? We take the transient data. So this is the first POD mode, second POD mode, vortex shedding, nice. This is the shift mode, essentially the base flow variation. Now we see a mixed mode. Then we see something like which corresponds a bit like to the second harmonics. Then we see a mixed mode, and then we see some other mixed mode. So the POD modes are not frequency pure, and they don't have to be frequency pure. If you look at the amplitudes, they are, the first three behave like in our essentially mean field model, our least order Gajokin model. Then we have some intermediate mode, so it looks a bit ugly, not very good. Now you can say, why did you take POD? And for the, I'm talking now for the experts, and why didn't you talk about DMD? Well, we did DMD. So these are the most pronounced DMD mode. The first one, the second one, the third one, essentially these have slightly different frequency, the other one. So we take the DMD mode, which contribute largest to the expansion. So essentially everything looks pure here, so it looks much nicer. Now there's of course a little but. When you do DMD, you have a linear framework. Essentially your expansion of the first mode will look something like that. You always have then, you have oscillations which are either increasing or decaying. That means if you would now extrapolate things right on the limit cycle, of course you will see you will get wrong results. If you go left from your data region, you will also get a wrong result. So the DMD can be very good if you are in the linear regime. It can be very good when you are on the tractor, but they're not particularly well suited on the in the transient regime. And then we have made a switcher between both, which we have called recursive DMD. I will talk about it later. What we essentially do, we require monochromaticity of the modes, but we found a trick to make these modes orthogonal. And then we essentially get near the similar resolution like POD, but we have a pure frequency behavior. So these are the corresponding amplitudes. The first three look as we expected. Then there exist some intermediate modes, and the other modes essentially contribute to a shape deformation and to higher harmonics. If you look now at the residual, so here you see the fluctuation residual. 1 means 100%, so you don't resolve anything of the fluctuation, and you go down 2 decades. If you look at POD, of course, it becomes increasingly better, but for a 1% energy error, you need 50 POD modes. So you have to let this sink. You have a two-dimensional manifold, and you need 50 POD mode for a 1% energy error, and a 1% energy error is a 10% amplitude error. So POD is something very nice, but may not always be the best thing to do. So this is essentially a credo that manifold models, you should consider manifold models. With a recursive DMD, we sacrifice a bit accuracy. We are not much worse, and we get a bit purer modes. In terms of the resolution residual, DMD modes are not very good, as expected. Questions so far? It's a good point. So the question is, what do you lose when you do LLE? And essentially, you lose nothing. If you are on the limit cycle, you can multiply the limit cycle with cosine phi, And then you have something, one POD mode with sine phi, and then you have the other POD mode. You can multiply it with cosine 2 phi, and you get the second harmonic, sine 2 phi, and so on. So essentially, you get all the POD modes. And if you, by the same argument, you can also get all the DMD mode, because essentially the DMD mode and the POD mode are both Fourier mode for the limit cycle. And so I would say the locally linear embedding is a generalization of it. Now, at some point, you may say, I'm cheating a bit, because we live on a two-dimensional manifold, but how is a two-dimensional manifold characterized? Well, we have 16 transients and 1,000 snapshots each. So we have something like 16,000 snapshots which characterize this manifold. So that means the data load on the reconstruction of the flow is very high, but still, the dynamics is two-dimensional. And there's a big difference between 2-dimension and 50-dimension. In 2-dimension, you can build a dynamical model, you can make an estimator, you can do a control, you can do everything. If you have 50 modes, essentially you just have a noise generation. With 50 modes, it's next to impossible to calibrate it and get a good prediction, do the control design with it, do the dynamic estimator in it, and so on. So sometimes these manifold models can be a real enabler. Any other question?
Yeah, I can ask a question about where you did the projection of the Navier slopes on the modes. What did you do with the pressure term?
Very good.
Did you ignore it, or you have separate modes for the pressure field? Just wondering how that goes.
So in this case, I've ignored it when I had a large domain. So when I have something like 15 diameters, then the pressure term is rather small. But the pressure term becomes very relevant if you have a short domain. If you have something like 6 or 7 diameters, then you have to include the pressure term, because the pressure term is either an energy source or an energy sink. And now the question is, how do you incorporate the pressure term? Now there are many possibilities. And you have alluded to one, namely you do the POD of the pressure field, and you put the pressure field in this Navier-Stokes equations, and you have one system of equations for the POD mode amplitudes for the velocity field, and you solve the other coefficients with the pressure Poisson equation. This is one possibility. Another possibility, actually, you can derive. You can derive an accurate pressure term representation for the POD modes. So this is what we did 2005 in 1JFM. This is another possibility. So if you ask Angelo Iollo, so Angelo Iollo essentially calibrated an extra term in order to account for the modeled pressure model. It turns out that in many cases, the additional terms which you have to add because of the pressure are just linear. I can tell you a couple more approaches, but I think this is now very interesting for you, but not for the big audience. So, last question. Good. Then we go to the next thing. Control. So, when you do analysis, so analysis is always very easy, because when you get dead data, you can always make a plot y over x, and the data cannot complain anymore. If you do dynamical modeling is a bit more difficult, because in the dynamical model you want to predict the future, and maybe you do not know the future. So you have an element of cross-validation. Now, at the moment you do control, you have a much worse situation. So essentially, you want to predict the future, but not only the future, the unforced future, but the future for many different actuations. And this is a very hard business. And in most of the cases, you will not have enough data for this type of control. So first, I will show you a case, the cylinder wake, of course, where we have this data. And the task is as following. So we cannot build the controller based on the Navier-Stokes equation, because if anything is larger than 10-dimensional, then the control methods typically blow up or become very difficult. So we would like to have a low-dimensional model of our original plant. So here you see the plant. B is our actuation signal, and S is our sensor signal. So it's sensor-based feedback control. We don't want to do it with the original plant, with the Navier-Stokes equation or the experiment. We want to derive a model before. And once we have the model, determining a controller is easy. And then we copy this controller from our model in our original plant. And the goal is always to optimize some performance, J. So essentially the model also must give the performance, let's say drag, lift, whatever, which we eventually measure. So now the task is build a model which contains the state and the actuation commands. You need some measurements equations. And from this, derive a controller which only reacts on what you know, namely your sensor signals. I will talk about the right-hand side later. So the right-hand side is kind of a shortcut, which is emulated in natural fluid mechanics. So here we go again, back to the cylinder wake. We have discussed this. And typical control problem is stabilize. So essentially reverse the Hopf bifurcation. Now we are at Reynolds number 100. The critical Reynolds number is something like 42, way above, lots of fluctuation. We want to go back to 0. And we assume now something a bit academic. We assume that we have something like a volume force here. So the volume force can go up and down. And we assume we do not know the whole flow field. So we emulate an experiment and we say we have a hot wire sensor further downstream. So typically the hot wire sensors is placed something like 6 diameters downstream, 2 up. So this is where you can measure very well the harmonic fluctuation. So now the name of the game is use this sensor signal essentially to predict the volume force. If you would have the whole flow field, everybody would know what he would need to do, right? So if the velocity goes down here, the volume force must push up. And if the velocity here is up, the volume force must push down. And at the moment you have essentially V equals 0, so no oscillation, you are done. So essentially the problem is very simple if you have full state control, but it becomes a bit complex if you have a sensor signal, because actually now you have to infer the state here. At the volume force. I could do something similar with a cylinder rotation, similar oscillation, and so on, but then the math will become more complex, and it does not serve the goal of this introductory lecture. So now, why are we interested in the stabilization? Well, one of the reasons is the drag. So when we look at the steady solution, the drag coefficient of the steady solution goes down, so from something like 2 to something like a 1 as you go from 25 to 200. At the moment you have a fluctuation, so these are the drag corresponding to vortex shedding. Suddenly the drag increases, and essentially if you can stabilize the wake, you can also reduce the drag. It's one means of reducing the drag. And sometimes vortex shedding is really bad. For instance, you have seen it in the Tacoma Bridge, so it can destroy things. And when you have the big bridges in Japan, they have feedback control. They have weights, big weights, moving inside the bridge to counteract vortex shedding. So far to the motivation. So. Now we go to our Gajokin model. I've shown you already our low-dimensional Gajokin model. It has 2 modes, say 2 POD modes and a shift mode and the steady solution. And what does the control change? Well, if you put in a volume force in the Navier-Stokes equation, a linear volume force with some carrier field and here's the actuation command, you get, surprise, surprise, another linear term here. After the projection. And here I show you a phase portrait, A1, A2, A3. The solid line corresponds to a DNS value, and the dotted line corresponds to our dynamical system. So it corresponds pretty well after a little bit of tuning. So far, not doing any control. We are happy with our model. Now, how do we do the control? Well, we have a direct numerical simulation. It could be an experiment. We only know what our sensor signal reads. So we have a single output, and we have a single input, so we control the volume force. And now we have to use this sensor signal somehow to do the control. Let's assume we know the state. let's assume we have full information control. So in this case, we would need to derive an actuation V as a function of A, such that the fluctuation energy, which you see here, has a dissipative dynamic. Let's say exponentially dissipative. Could this work? Well, we have A1, A2, A3 is slaved. We have B, so we are in a three-dimensional phase space. We have two evolution equations from our Gajokin model. So we have one wish free. So our wish is now to have a decaying fluctuation rate. And with this, we can in principle derive our controller. How? Well, let's take our original Gajokin model. We have again polar coordinates. These are the original lambda equations. And this is essentially projection of the volume force term. So you see, if you want to decrease the fluctuation energy, then our actuation must oppose somehow this phase here. So we are not interested in the frequency. And there are techniques of doing that. Energy-based control, I will talk about it later. But you can see, in principle, it should be reasonably simple to define a controller where you get a dissipative dynamics. Now we have another problem. We don't know the state. We only know, or we pretend that we only know the single sensor signal. So somehow we must determine from the single sensor signal the full state. And this looks impossible. We measure the u velocity at one point, and we want to determine the whole velocity field. So it looks like we are violating the principle of the implicit function theorem. So we want too much, but actually we know much more. Number one, we know the whole trajectory. Number two, we know also the dynamical system. So when we start somewhere, we know where the trajectory goes. And so actually we know much more than this single point. Could this be enough to determine the state? Well, if you look in the past, the answer is yes. And the main idea is shown here. You have a Gajokin model, which I've shown here. So we add an additional term, and if our sensor signal, which we measure, equals the sensor signal, which we predict, then we don't have to do anything. We can advance the estimated state with the original system. So everything is fine. If our sensor signal is different from the sensor signal we measure, so in this case we have to do something, and we add a linear term. Now there exist some tricks how to determine the L in such a way that the error which we make in the estimate of A and the full state A decay exponentially fast. So this is a dynamic observer, and we can use this essentially to determine the state. So here we do it, sensor signal. So we have the history. So this goes now in the past. And essentially, using this history and the dynamic observer, we can point a location on our paraboloid. So with that, we can now determine estimate the full state from the sensor signal, and we know how to actuate for the full state. So we have a control design. How does it work? Well, we start. So this is the vortex shading. You see positive and negative vorticity here. When we do the control, we lose about 30% of the fluctuation energy. And so we go on the paraboloid a bit down. So something must have gone wrong, right? If you ask our model, we can stabilize a fixed point. But if we look at the Navier-Stokes equation, we cannot stabilize the fixed point. So one thing which has gone wrong is the following. As a control is active, the wake changes, so the phase relationship between the sensor signal and our volume force changes. So this is not taken into account in the POD modes. So the POD modes somehow must follow our success of the actuation. Now we can get the idea, okay, we do the POD and do it with updated POD modes, then we can take 50% reduction, we can continue these things. At some point, we end up at 60%. It turns out 60% is the optimum. You cannot stabilize the flow. What is the reason? Well, if you have a volume force here, it's essentially like elongating the bluff body. So essentially, you just delay the vortex shedding. You do not have the full authority to stabilize the flow. So you see now the Gajokin model must be wrong, because it tells you can stabilize, but actually you cannot do it. And this gives you an idea of the possibilities and the troubles which we are in when we just have the naive cylinder wake. Any questions? Well, what you do, good question. So first you update the kinematics. So you take the controlled flow, you take the PUD of the controlled flow, then you put the changed PUD modes, do another Gajokin projection. So you also change your dynamical system, and then you do the control again until you hit another plateau. And essentially, the purpose of the control is to destroy the validity of your model. So if you see the same coherent structures after the control, then you have done something wrong. So this is kind of a warning sign. I want to make you aware of the troubles you can be in model-based control. And I will now tell you another thing. Suppose, for instance, you go from a natural state to an actuated state. Good. Now, what happens? You can model the actuated states. You can model the natural state, but of course the PUD mode won't correspond to each other. You have destroyed your original flow. Now, what can you do? Well, you can figure out which modes are stationary as you go from the natural state to the actuated states. One set of modes. Which modes do you have to deform? For instance, in case of the cylinder wake, we have to deform the vortex setting. The vortex setting changes under actuation. So you have to figure out something like a flexible subspace. Then there are some modes which you will add during the transient. For instance, if you do high frequency forcing, enrich the mixing layer to stabilize the wake, then you have to add these modes. And then you have a decaying cylinder wake. You can stop your actuation. So doing the transient from the forced flow to the stabilized flow, you can stop some modes. But maybe you have to add some other flows. So even for this simple case, you are in trouble. As you are going from an actuated state to a natural state, it's very difficult to describe it with one set of modes and doing a control-oriented model. And with that, I want to conclude with a solution of this problem, which we have called machine learning control. So let me look. Yes, wonderful. Look at this beautiful eagle. He's landing on a stone under gusty wind condition, very successfully so. And he can do so with external turbulence, with can do so in rain, can do so with a full stomach, empty stomach, maybe an injured leg, whatever. So he does really solve one amazing flow control task. And let's assume that we built a flying robot. and we have to emulate what this eagle is doing. And we will get in trouble with a model-based control. So somehow this eagle must have learned his flow control tricks. This is one of many. In another way, like going to a university and learning the Navier-Stokes equation, doing reduced order modeling, learning control, making the PhD or becoming a professor or whatever. What is a nature's way? Well, nature works with trial and error. And this is based on the idea it's very difficult to predict the effect of actuation, but it's very easy to see if a given controller works. So this is I'm shown here. So we have, again, a plant, a controller, and so we add a controller, and we look how it works. And then there's some box, machine learning. Essentially, this box optimizes. So we are always using one generation of controllers after the other until our performance becomes better and better. Can go back to the full screen. And the cost functional is typically related to the state, so it could be the drag, and there's something like an energy penalty, so you don't want to actuate too much. And the problem which we solve is a regression problem of the second kind, or variational problem. So essentially, we do not want to go this path, but we want to determine a controller in such a way that the cost is minimized. And so this is, in quotation marks, nature's way, which has been pioneered by Ingo Reichenberg before I was born, namely in 1963. So he developed the evolutionary algorithm at the TU Berlin. And he showed how you can do passive design, for instance, have a design of an airfoil for lift optimization with statistically randomized approaches.